Hello and welcome back to AP Chemistry, everybody. This is beginning of Unit 4, where we're taking a look at the types of reactions that we find going on. Now, in general chemistry, we tend to talk about single replacement and double replacement reactions. We talk about synthesis and decomposition. Then we talk about combustion reactions. And in AP Chemistry, things are a little bit different. We recognize three different types of chemical reactions. And don't worry when you see something that's a little bit different. When we talk about precipitate reactions, really what that's saying is we see things like right here. We're mixing two aqueous things into form a precipitate or a solid. And really, if you've had general chemistry before, what that means is you got a single or double replacement going on. So it's a lot of the same stuff, but we're going to be throwing in some other terminology, things called redox reactions. Taking a look at charges of things and goes a little bit deeper into it, foundations and things that we've had in general chemistry. So we're going to take these one by one, and the nature of this particular video is talking about that first group of precipitate reactions. And specifically with that, we're taking a look at different things that are going on within a reaction, and we can talk about it in terms of concentrations of things. And so we get into this a little bit, and this will be familiar for some of us because we've covered molarity and so on and before. But really what's going on in a precipitate reaction is we have some kind of container. Maybe this is a beaker, maybe this is some kind of reaction well or whatever. But if we have, for example, in a diagram, that these particles that I label with X's, this is going to be my water. And so those would be things like solvents, the things that do the dissolving. And I'd have other particles in there that would be my solids. And so this might be salt, this might be sugar, and so on. We refer to those things getting dissolved as a solute. Okay? And so what's happening within this reaction, or within this situation, is I might have a chunk of a solid in here, and we have water molecules that are around there. And what's going to happen is as these two interact with one another, the water is going to dissolve out some of the solutes and actually not really bond to it, but form a small attraction to those. And we'll get into those attractions later on. But it's basically just visualizing what's going on within this. Now, when we talk about this in terms of precipitate reactions, really a short way to do this is to talk about solution chemistry. Okay? The chemistry of what's going on within those solutions. Okay? So one thing that we need to wrap our head around is this concept of molarity. Molarity is a function of something that is a ratio of our solute to our solvent. And there's your equation. Now remember, in this case I just showed you, my liters of solution, that's going to be my solution total. And when I have these solutes in there, we measure this in terms of moles. And we just say, basically, how strong is this? How many particles of this solute are there in the entire solution? And that's where this uppercase M that's italicized, that's what molarity actually stands for. Okay, just wrapping your head around there. Let's take a look at what this might look like if we're doing some calculations with precipitate reactions. Okay, in other words, we're going to do some solution chemistry. So let's take a look at the first one. We're seeing that we have 11.5 grams of sodium hydroxide in 1.5 liters of water. Okay, 1.5 liters of solution. And the question is really, how strong is this? Okay, how potent is this? So for this particular problem, you see we have two components. We have moles and we have liters. And just keep in mind that we're always solving for M. When they ask about what is the molarity, that is the capital M. So let's go ahead and take my 11.5 grams of my sodium chloride, or in this case, sodium hydroxide, and let's convert that to moles. Okay, grams of sodium hydroxide into moles of sodium hydroxide. And remember how we solve for moles. I break down my molar mass. I see that I have one sodium, I see that I have one oxygen, and I have one hydrogen. Well, the formula mass on my sodium is 23, 16, and 1. So the entire formula mass is going to be 1 mole's worth is 40 grams. That will give me, let's see here, 0.2875. That's moles of my sodium hydroxide. Now it says in the problem that I have 1.50 liters of water. Well, remember we have liters of solution, so let's take my my 0.2875 divided by that 1.5 liters. It's already in liters, so I don't have to do anything with that number. Okay, and so what I end up with is a molarity of 0.192. My label would be M for molar, and it's sodium hydroxide. Remember, AP College Board is always looking for the work. Please put a box around the end so they can see what's going on with your problem. Now, in the second one, we see that we got a couple things we need to address. First of all, I have grams of zinc, so we need to take care of that. And I have milliliters of water, so I have to take care of that as well. So here's my 6.2 grams of zinc chloride. And here I have 1 zinc, and I have 2 chlorines. Okay, so if I look on the periodic table, I look up the mass of zinc, I look up the mass of chlorine, I double it, and I find that with my formula mass, I end up with 136.4 grams of zinc chloride per mole of zinc chloride. So the first component of this will give me 0.04545, and that's going to be moles of my zinc chloride. But I also have 450 milliliters of water. Remember, if I have 450 milliliters of water, I need to convert that into liters. And 1 liter is 1,000 milliliters. So essentially, I'm moving my decimal 1, 2, 3 places over. That gives me 0.45 liters of water. And so there's the little trick. Got to convert your liters to milliliters, isn't it? So I end up with a concentration of 0.101 molar zinc chloride solution. Okay, so pretty straightforward. Nothing too tough behind that math as we go. Now let's take a look at some other examples along the way. And let's look at example 2. Calculating the moles of zinc when we have solution B. Now remember, in solution B, we had a concentration already. Okay, we saw that we had, it was a zinc chloride solution, and we knew from the problem before, we knew that we had a 0.101 molar zinc chloride solution. Okay, so this gets a little bit trickier with just keeping our wits about us. Now, we want to find the moles of zinc ions as well as chlorine ions, but here I've got both, don't I? So in the solution itself, I have zinc chloride, and I find within zinc chloride, that will dissociate into 1 zinc ion and 2 chloride ions. Okay, remember it's an ionic compound, so when in solution, it'll dissociate into those ions. It's a 1:2 ratio. Okay, so now I've got my pieces behind all of this. I know that the strength is a 0.101 molar solution. What that means for us is that I have 0.101 moles of zinc chloride for every 1 liter of solution. Okay, now I know from the problem before that I didn't have 1 liter of solution, though. I had 0.45 liters of solution. So I have to accommodate for how much was in there. Okay, once again, the molarity that I calculated was 0.101 for every liter, but I don't have a liter. In fact, I have just less than half. So what that tells me is I have, after I do my math, a 0.04545 moles of zinc. We knew that actually from before, didn't we? Okay, so we calculated that out. But here's the trick and why I did my balanced equation. Notice that for every 1 mole of zinc chloride, I had 1 mole of zinc ions. Okay, so really what that's saying is a 1:1 ratio, so I have 0.04545 zinc ions. Okay, at least in terms of moles. I should put moles in there. That's how many zinc ions I have. Now the nature to their question, because I also have 0.101 molar solution. That's 0.101 moles of zinc chloride per 1 liter of solution. I didn't have 1 liter of solution, did I? I had 0.45 liters of solution. And so I get 0.04545 moles of zinc chloride, but now I'm addressing the second part of the question. For every 1 mole of zinc chloride, I have 2 moles of chloride ions. And so I'm going to end up doubling this. And so when I do that math, I end up with a 0.091 moles of chloride ions. Okay, so that just solves that particular question. Now let's take a look at the next example here, where I take and I see that I have a given concentration of 0.14 molar sodium chloride solution. What volume of blood now can I get from 1.0 milligrams of salt? Now remember what molarity is. Molarity is moles of solute over over liters of solution. So what do I need? I need to solve for this. I'm given this, and I've got 1.0 milligrams of sodium chloride. Now be careful here because it's milligrams, not grams. So let's deal with the components in here. Let's deal with my milligrams of sodium chloride. Let's get rid of milligrams of sodium chloride, and let's get it into grams of sodium chloride. Then I can go from grams of sodium chloride into moles of sodium chloride. Okay, 1 mole, this ends up being 58.5, 23 plus 58.5. Pen's not keeping up with me. I see that I have 1 gram is 1,000 milligrams. And so with this, I end up, let me see here, with a number of 1.7 times 10 to the negative 9 moles of sodium chloride. Not very much, but I only had 1 milligrams worth in the first place. Now, remember, I'm given my molarity, I'm given my concentration. So let's take that 0.14 molar equals my 1.7 times 10 to the negative 9 over X liters. They are saying just volume, so let's assume in liters. If they ask otherwise, we'll deal with that later, right? So let's get X by itself. There, it's gone. And so to get X by itself once more, I take 1.7 times 10 to the negative 9 divided by my 0.14. And so I end up with a volume of 1.22 times 10 to the negative 4th liters. Okay? That ends up being, you could say, you don't have to, or 0.122 milliliters. Either answer works. I would not go in the extra work if they just say volume. Leave it in liters. So that's how you solve a problem like that. Okay, now that's just going through precipitate reactions and seeing how we do molarity from those. All right, let's take a look at another way we can look at this type of precipitate reaction, but this is when we have some liquids already, and we refer to this as a dilution. Okay, so the solids, we approach in a little bit different way. The solids we're going to be approaching through that molarity part. Okay, we can pick apart that a little bit. And we also have liquid ways of doing this, if they're a liquid rather than a solid. So let's take a look at them in turn. Let's say we have a solid here, and we have, let's see, we need 750 milliliters of a 0.2 molar potassium dichromate solution. Now you guys get to get into my shoes, where I have to make up all these solutions for you guys to do lab. And the question is, how do I do that? Cr2O7. How do I make that specific concentration? I know I need this much. Okay. Now remember, molarity is moles of solute over liters of solution. Okay. So this is actually an extension of what we just did, isn't it? So we end up with 0.2 molar. And I need to find my X moles of potassium dichromate. And I'm given my liters of solution already. Be careful, this is a 0.750 liters of solution. You can't say 750 because that's milliliters, isn't it? So let's solve for X. I multiply both sides by my 0.75. I end up with X equals 0.15 moles of potassium dichromate. Well, if I'm going to physically make it, I don't break out my molometer, I break out my balance. And so then I figure out within that moles of potassium dichromate to grams of potassium dichromate. Okay, and so if I just do that math real quick, I see that I have 1 mole is 294 grams. 2 potassiums, 2 chromiums, and 7 oxygens. So I end up with an ending mass of 44.1 grams of potassium dichromate. Now be careful. That did not answer my question. I need to make this. How do I make it? So I have to finish the thought. I start with this 44.1 grams of potassium dichromate, and then I add my solvent, what I would assume water. I would add that to my 750 milliliter mark. That finishes out the problem. I actually don't know how much water I'm going to add because this will displace the water. So I would have to just fill it up to that mark. And remember with this, we always want to say that if this is my 750 milliliter mark, I want to reach the bottom of the meniscus hitting that 750 milliliter mark. Okay, so that's what we do when we have a solid. But what if we have some liquids and we want to actually take, for example, a big old jug. This is what we've got in the back of our chem rooms. We've got a big old jug of really strong sulfuric acid, H2SO4. By really strong, the strongest we can order is 16 molar. This is what we refer to as a stock solution. Okay, we've got a lot of this, but we need to make, let's see, a liter and a half of weaker solution that we can actually work with. So it's a 0.25 molar solution. And so the question is, how do I do that? I need to pour out some of this and make this solution. All right, so here's your equation for that. When I'm doing liquids, I take the strength of one thing and its volume, and I figure out the ratio to strength of my weaker thing and its volume. M1V1 equals M2V2. Pretty simple. I'm going to actually figure out and plug in my numbers. I have a 16 molar stock solution. I don't know how much I'm going to be pouring in. Okay, and notice it's just volume. That could be in milliliters, it could be in liters. The problem doesn't specify. Since this is given liters, let's stick with liters. So the strength I need to get it to is 0.25 molar, and I need 1.5 liters worth. So if I'm solving for this volume, I'm going to end up with 24.3 milliliters. Okay, the reason I went to milliliters, it was actually a 0.0243 liters. And you can say that, guys, that's fine. Once again, I'm not done. This is my stock solution. Now, I actually want to be careful in my wording here. I'm not sure how picky the College Board is going to be, but we need to say that we add acid to water. Just like you oughter. Just like you ought to. So we add acid to water just like you oughter. So you don't take my stock solution and add water to it. You actually take your water and you add it to, since these are liquids, we know what they're going to add up to. We're going to add to, if I end up with 1,476 milliliters, I add it to 1,476.6 milliliters of water, because that will then add up to my 1.5 liters total. Okay, so that's just kind of part of it. Actually pretty simple when we get into dilutions. We solve acids and bases, strong acids and bases in a very similar way. So this is a pretty simple equation to be working with. And honestly, that is just about all you need to know for this first section. We're going to be diving into other things that tie into this, but your first set of problems is just going to be working on that. Okay, you guys have good luck.